Okay. Hello, everyone. Welcome to Lunchtime Scientist, a series of Q&A sessions with working scientists organised by the Geological Society, Linnean Society, Royal Astronomical Society, Society of Antiquaries, and the Royal Society of Chemistry. I'm Amy Ball from the education team at the Geological Society, and I'm excited today to be joined by Divya Persaud, a planetary geologist studying for her PhD at University College London. Divya has previously worked on various research projects in planetary geology, from impact craters on Saturn's icy moons to meteorites and the surface geochemistry of Mercury. Today, her work focuses mostly on Martian geology. Divya is going to speak for around 10 to 15 minutes about her current research. And then afterwards, you will all have the opportunity to ask some questions by using the chat box. Okay, so without further ado, I'm going to pass over to Divya. Hi, Divya. Are you able to share your screen?
Yes. Yeah.
Excellent.
And do that. Awesome. So, hi everyone. Thanks so much, Amy, for that introduction. So today I'm going to be talking to you about 3D visualization of geology on Mars. So just speaking as a geologist, and what does planetary geology even mean? So normally on Earth, when we study geology, we go out to a field of interest. So this might be the mountains, this might be the ocean, this could be a dried up riverbed or a coral reef. And we take detailed notes of what is there. We do measurements. We're able to take samples and do all sorts of different types of analyses, maybe about the chemistry or the color or how the rocks look or how they interact with life. And all of this is done in 3D. So we as human beings are on the surface of a planet and we look at these things in 3D and we understand them in 3 dimensions. But planetary science is really difficult because all of our data actually comes from space. So aside from Mars rovers, our images for example, Mars are actually taken from orbit. So here's a little animation from NASA of a satellite that takes images of Earth, actually. As you can see, these satellites zoom around the planet and then they get a really, really long strip of an image. And these images cover a really wide area. And so this is what we have to understand the geology of somewhere. So we're not on the surface getting to look at things, pick up things, measure things with our hands or with hand tools, but we actually have to look at not only just two-dimensional pictures, but two-dimensional pictures taken from space of a really big area in a map view. And this really changes how we do the geology that we want to do. So if we want to understand the surface of Mars or the moon, we have to be a bit creative. And so my work goes into how we can turn 2D images into 3D images and sort of simulate or pretend as if we are on the surface. And this can help geologists really get a good understanding of what's going on these planets. So 3D images are really cool because they're actually based on how our brains work. So our eyes get 3D information because we have two eyes, and our eyes aren't just stacked one on top of the other, right? We have a little bit of space between them. And that means every time we look at something, each of our eyes is getting a different view of that object. So it's a slightly different look. So if you pick something where you're sitting and say, okay, I'm looking at a glass of water and I close one eye and then I close the other eye and I alternate between them, the glass kind of moves, right? So these are two different pictures, but of course, when we're looking at something, we only see one picture. So the second thing our body does is that our brains process that information, the two images, Plus it uses other clues. So our brains are really cool. We can get a lot of information that we don't even know we're getting. And some of that information is understanding how light bounces off the glass, or sort of feeling how far away we are from objects, and looking at the shadows of an object. And using all that information plus those two images, our brain understands this object as in 3 dimensions. So if we reach out, we can grab it. And that is depth perception, right? Perceiving how far away something is and the shape of it as well. So that's how our brains do it. But so how do computers do it? The computer can take 2 images of the same area that are taken from slightly different places. So pretend one image is from one eye and one image is from another eye. And on the right, I have a satellite image of a river on Mars that I'll talk about later. And it's flickering between the left eye image and the right eye image. So we have the 2 images, and then the sort of brain processing that we do is done by really complex computer programs that look at where the satellite is in space, how far it is away from the planet, the location of the sun. So if the sun is low in the sky or really high in the sky. So very similar things that our brain uses, and then puts all that information together and is able to turn that 2D image into a 3D image. So I'm going to show you what that looks like in different places. So this is a 2D image of a crater on Mars called Victoria Crater. And this is where Opportunity rover explored during its very early days of its 15-year mission. And I'm going to show you a video because this is an actual 3D model that I visualized. So we're zooming into this 2D image. It's in a software that can interpret 3D images. And so we're able to actually drop into this crater and see it in 3D, which is really cool. So look at all those cliffs. You can see how steep they are. You can see these ripples on the floor. There's Opportunity rover in an image. And we get to actually appreciate how deep this crater is. And as a geologist, this is great. This is like something I could see if I go out to a crater on Earth, or a sandy desert on Earth as well. Even though it's in black and white, there's just so much information there, and it makes so much more sense to the human brain. So here's another one. This is a little visualization I did recently of some mysterious plateaus on Mars. And so we don't know how these formed, whether it was in water or wind or ice, but 3D visualization tools are really cool because you can actually zoom around and kind of play with terrain, but then also your brain still understands it in a 3D way. Here's an animation I did of the moon. So this was a 3D image processed by someone in my group as part of a project to support NASA in looking at potential landing sites for human astronauts. And this was just a little flyover of this crater. And you can see how bumpy it is, right? And this is really, really important because if we want to land people on the moon, we need to know how bumpy it is and find a smooth part, essentially. So not only a smooth part for people to walk on, but also a rocket to safely land and take off from. And that's a really important set of questions as we think about not only landing on the moon, but landing on Mars. If we want to land spacecraft or people, we always have to think about safety, and 3D helps us do that. And so some of my work has been on icy moons as well. And so 3D helps us with a lot of things. And this is one little moon of Saturn called Mimas. It's a very, very, very tiny moon compared to our moon. And it's mostly made from water ice. And one of my projects has been looking at craters or very big basins on these types of moons, which can tell us a lot about whether these moons once had subsurface water oceans or might still have those oceans, which has could tell us maybe that life possibly could exist in those oceans. So it's a really exciting thing, and 3D gives us that extra information where we have very limited images. And I included a little picture here because Mimas is called the Death Star moon, so you can kind of see how it's similar. And then finally, here is the Curiosity rover landing site, which I'm going to be talking about. So this is an animation I did. So Curiosity is slowly climbing up this mountain right here. And this big slope is part of a bigger mountain called Mount Sharp. And it's really exciting because all these features are kind of mysterious. We don't know that they've been formed by water or ice or wind or a combination. You can see all these really interesting features and sort of bumps and hills. This looks like a big stream that could have been water. So as Curiosity has been slowly climbing up, it's been taking samples of rocks and looking at their chemistry and their color and their shape. And a lot of these rocks seem to say that this landing site, Gale Crater, was a lake, which is really cool because we're looking for life on Mars or signs of previous life on Mars. So we want to know how long water actually was on the surface. So if you have water for a really short period of time, life probably didn't have enough time to evolve. But if water existed for a couple billion years, maybe little forms of life like bacteria could have evolved. So that's kind of Curiosity's main question. And that's also going to be Rosalind Franklin rover's question from the European Space Agency. And so all of these questions are really interesting and fascinating, and that's kind of why we need to try to get as much information from these 2D images in 3D as possible. So I'm talking about Gale Crater, and I mentioned the mountain. So in the upper right, here's a little 2D map, and this is where Curiosity is just about now. And this is this mountain right here shown in 3D, and this is called Mount Sharp. And so one big mystery of Gale Crater, not only how long water survived, but also how this big feature formed. And we just kind of don't know. It doesn't really make sense that it's there. It should be eroded by wind by now. So what's going on? And I'll sort of walk you through how we can look into the history of this interesting mountain feature. So here's that 2D map again. And I've highlighted a little thing right here. So if you notice, there's this sort of river feature going right here that is quite huge. And this is high resolution imagery from there. And this is a 3D image that University of Arizona made, and which I've sort of manipulated for my own use. And this river is super cool because not only does it show definitely that, okay, water formed this, lava couldn't have formed this, wind couldn't have formed this. This was a really high energy river on Mount Sharp in Gale Crater, probably filling this lake. But what's cool is that you see all of these lines, these dark and light lines in the sides of the river are rock layers. And in geology, the deeper you go into the rock record, the further back in time you're going. And I'm going to explain that in a second. So these rock layers are a time capsule into how this area formed. So if we are able to study these layers, we can actually go back in time and kind of figure out, okay, what formed this? Was it water? Was it wind? So that's before the river cut through it. And so here is a 3D video of that channel. So again, you see these really clear layers. You see giant cliffs. This is about 2.5 kilometers wide. So this thing is very huge. It's about 800 meters deep. And just notice these exposed bright bits and the dark bits. And they're also alternating. So there's something that we can think about with, okay, was there a repeating event? Was it maybe a lake rising and falling with water? So there are the repeated layers again. Was it a lot of wind and then a sort of still period? Was it a lot of rain and then a really dry period? So this is really exciting to see as a geologist. And then we have all these really interesting and kind of weird and funky features cutting through it as well. And something also cool right here is an island that was once forming while the river was flowing, but didn't quite completely separate from the sides. So it's super cool to think to look at this as a geologist and see a riverbed, but also seeing all these really, really fantastic layers that are actually going back in time. So what does going back in time mean, right? So rock layers are ideally horizontal. So if you think about sand falling through an hourglass, but on a really large scale, it kind of falls evenly. So if those layers are disrupted in any way, so in the upper right, I have an animation of rock layers being squeezed, and you're seeing those horizontal layers slowly changing shape and becoming Z's. And on the bottom left, I'm showing a dune that's migrating. So there's wind blowing and the sand dune is moving. And you see these yellow stripes. Those are actually the layers, and they're slowly moving and migrating. So you can see that in the rock record as well. So these different shapes in the layers can tell us about how that rock has changed over time, whether it was wind, whether it was something structural like an earthquake, or whether it was water, whether, again, if it was a lake rising or falling, and or an ocean tide coming in and going, if there was a seabed, or if it was a river that flooded and then dried out, and flooded and dried out, that kind of thing. And because they're ideally horizontal, the oldest rock should be at the bottom and the newest rock should be at the top. And so again, if you cut through this, and here's an animation of a river channel sort of forming, and you're seeing these layers form. If you're cutting through it, you're going deeper and deeper into the older rock. So if we look here, we want to be able to study all the layers down here all the way through the top, and that can give us a really good snapshot over time of how Mount Sharp formed. So this is kind of how I did this work. I'm using software that was built for Rosalind Franklin rover to study rover images in 3D, which is a completely different topic, but kind of cool. So this is the Rosalind Franklin PanCam team, and PanCam are the eyes of the rover, and they're being, or rather has been built in the UK by UCL and some other universities. And PanCam will be able to take 3D images from the ground, just like a geologist. So these are really important. And the software has been built ready to receive those 3D images so that we can do geological measurements from them as if we are in the field. But I thought, okay, what if we put these orbital 3D images in the same environment and actually do all the types of things a geologist would? And so that's what I've done. I've looked at all these different layers. I've divided them up into possibly different sort of events that put them there, going through this section of time. And then I've taken measurements, so I've color-coded them, and I'm sort of tracing out and annotating these layers throughout the entire channel on both sides to see how they relate to each other, whether they're harder or softer material than other parts, and also seeing how they are oriented in 3D. And so what does that mean? So if you look at these layers that are going through the channel, and we look at, so this is a tool that lets us put a 3D sort of disk or plane through all of those layers. And we can see whether some are sort of tilted one way or the other. And that can tell us, as I showed before with the animation of those rocks getting pushed and pushed into Z's, how maybe certain events cause certain rock layers to be tilted, or if maybe they were all deposited very horizontally. And that can actually tell us, was it wind, was it water, was it something else? And so a lot of these results are actually really pointing to a sort of lake environment, which is really exciting because that means a lake existed during this whole section of time. And that might be millions and millions of years, which is really promising. And I just wanted to end with a bit of a view. So I've put a little astronaut right here. So I want you to pretend being in this channel, it's so easy for me as a geologist to look at all this 3D data and sort of lose perspective about how big it is. And so I put this little astronaut, and we're just going to fly out and look at this channel together. And I want you to imagine what it would look like standing on the edge of this cliff and looking at this magnificent river channel. And so I'll play that. So it brings to mind a lot of places on Earth, but there's also something really special and really different about it. And it's exciting to think that maybe someone will have this view one day. And with that, I'll leave you with an image that I made using that view. The astronaut is actually there. It's right there. It's very tiny. And I simulated this image using a sunset from Curiosity rover. So dusk on Mars is actually blue instead of red. And so I cast this sort of bluish light over this red and brown river channel. So this is what you might see at sunset standing on that cliff. And that's all I have. So thank you so much.
Thank you so much, Divya. That was so interesting. It's amazing to see how we can have 3D images on Mars. I never even knew that was possible. We have a few questions that have come in. Ah, yes, your video. Sorry about that. That was my fault. Okay. We've had some questions come in. Helen says, does Mars have a core like the Earth?
Yes and no. Mars probably had a core a lot like Earth's. So Earth's core is sort of a mix of materials, and you have a liquid iron and you have solid iron, and those two iron layers are spinning, and that's sort of generating what our magnetic field is. And Mars rocks actually have signs that they were magnetized at some point, but there is no active magnetic field. So the idea, I think, right now is that at some point in its history, Mars had a core a lot like Earth's that generated a nice magnetic field around it. And over time, that liquid iron probably solidified and that magnetic field disappeared. And so you don't have the magnetic field anymore. Yeah.
Cool. Eleanor says, how do we know these features, rivers, etc., were formed by water and not by another liquid?
Yeah, so I guess we don't know quite whether it was water exactly. We know that it was some sort of liquid that was not lava. So we can tell that a few different ways. One, comparing to Earth, which is a bit difficult because Mars is very different than Earth. It's a lot smaller and its gravity is less. But we do know from studying, say, fjords formed by glaciers and also rivers formed from really low energy or high energy flows, from channels carved out by lava, what kind of shape they kind of take. So it's based on the underlying physics, and we can replicate that in the lab as well. So sometimes you can't tell, and it can be very controversial to say it's water. So in a lot of places on Mars, you can't tell. I think with something that is very stark like that channel, it's pretty convincing that it was water, or at least like an icy, slushy sort of water. But lava wouldn't cut through that kind of way.
Nice. From Josh, how do rovers like Curiosity analyze the chemical compounds in rocks? Not quite your area, but I'm sure you know a lot about it.
That's a great question. So they kind of think of it as sniffing. So they ingest bits of rock. So they might have some sort of scoop that is taken into a gas chamber. And so Curiosity is actually called Mars Science Laboratory. It has a little laboratory inside. And the rock is actually combusted. So it is vaporized under high heat and pressure, turned into a gas. And then using different tools, you can analyze the spectra of that gas. So that gives you a breakdown of all the chemical compounds in that gas. So it's the same way that we would do it on Earth. It's just very, very small and very low energy.
I like the analogy of sniffing. For those interested in going into this field, do you have any advice? What courses to take? What resources?
Oh, yes. My go-to advice always is find a path that you enjoy. So planetary science is an entire mix of computing, engineering, planetary geology, pure physics, astronomy, chemistry, visual arts. So if you are interested in space, find the part of it that that most interests you, and also figure out like what you enjoy doing. and there's so many ways to get into it. So find a way to direct that. So if you are interested in astronomy, it's kind of clear. But if you're more interested in engineering, or if you're more interested in art, there are a lot of resources into how, for example, a lot of Mars rovers operators came from the art end and doing 3D visualization for the public's sake. So find something that you're passionate about and make that about space, I think. As for courses, I think it's always important to do like introductory astronomy or physics. Geology is really helpful, and I don't say that just as a geologist. It's such a great and like really sort of tangible way to understand the physics and chemistry of everything without really getting into like all the sort of nitty details if you don't really like all of that. And then computer science is always useful as well.
Lots of different ways into it.
Mm-hmm.
Given the choice, what would be your first site on Mars that you would want to visit as a geologist?
Oh, good question. Oh, so many places. I think maybe the poles. The poles are really cool, and they change across the seasons, and you get really funky features that like grow and shrink, and you get explosive geysers. It would be really dangerous. So maybe not there, but that's what I thought of first.
What are the poles made of? Is it ice?
It's CO2 and water ice, usually a mix of that, yeah.
Cool. How much maths do you use on a daily basis when you're working with these 3D images?
I'm gonna give you a secret. I work with no math. I love mathematics, but I don't use it really all that often. I do a bit of quantitative stuff. So when I do the measurements of the layers, I'm getting angles. I have to do some trigonometry for that. But for the most part, when I'm doing processing, other people have built these processing tools. So whether in our group or by other people. And so I don't really even work in the computer science sort of realm. So it is a limited amount of like arithmetic and trigonometry. So if you're scared of math, there are things for you to do.
Doesn't need to be limiting. Which part of geology on this planet interests you the most?
I've always been a big fan of volcanoes, and I guess that's also why I'm interested in icy moons, because they have ice volcanoes, and I think that's cool. Also, I would say, I mean, I grew up around a lot of glacial geology. I've always been interested in glaciers and the sort of features that leave behind. So we lived by a creek that was formed by a glacier. So yeah, that's something that I really like to appreciate when I go out in nature, at least, but also scientifically.
What one have we got now? Sorry, there's lots of questions coming in. People are very interested. Do you think Mars has any metallic ore bodies?
I'm not quite sure what that means. Sorry.
Yeah, I think it's more of a sedimentary situation, Mars, isn't it? I don't know, I guess. Do we really want to be trying to mine other planets just now? I'm not sure. We'll leave that one. Someone has said, how do ice volcanoes work?
Yeah, ice volcanoes work in a lot of the same ways that lava volcanoes work. So if you take a really cold body, so icy moons are so cold that the ice that forms their surface and their interiors are as hard and sturdy as rock. And so if you get any sort of melted or slushy ice, or even slightly warmer ice, it will behave like lava. And that pressure can increase in the subsurface, and then it can break and fracture and erupt out of the surface. So it's slightly different in that usually, so there are no plate tectonics on these bodies or anywhere else in the solar system to our knowledge. So for moons of Saturn and Jupiter, when you see volcanism, or you see, cryovolcanism, you see these water ice volcanoes. They're usually caused by these moons having a really sort of strained orbit around their planets. And so they come closer, and then they come farther away, and then they come closer. That puts a lot of stress, and they kind of go like that throughout their orbit. And that causes a lot of heat in their interior and can melt some of the insides. And some of them, we understand their oceans having formed in that way. But also all that stress will cause fractures on the surface. And so you have the heat, you have the liquid, and you have the fractures, and that pressure builds up, and then you get the eruptions.
Okay, back on to what classes did you take in school? Where did you do your geology degree, and how did you get into geology?
Yeah, I did my geology degree in the US at University of Rochester. So the classes that I took, I took in school. And how did I get into geology? That's sort of a combined answer. So I got into geology because I like collecting rocks as a kid. And my mom said, you could be a geologist. And I took that really seriously. And I read all these books about geology as a kid. And then I saw some TV programs about planetary geology. And I thought, okay, that's what I want to do. Because I was interested, I made NASA my homepage and I read about this all the time. And I was a big nerd about it. But when I started university, I started a geology degree, and I also immediately started doing research. So I joined a research group. I did some research before university as well. So it's not so much getting into research early, it's just finding ways to figure out what you want to do. And the best way to do that is by trying it. And if you can't try it, then at least read about it and see what grabs your attention. And then the classes I did in school, so I did the US school system, it's a bit different, but my final year courses were chemistry and calculus, but also English literature and Latin. And I felt that that sort of well-rounded education was really, really important, especially for planetary science, when you're working with people from completely different disciplines, to actually be able to think in different ways and not get too bogged down in what you're doing. So I think that's really important.
Yeah, you can get into geology in lots of different ways. There's not just one direct path that everyone has to follow.
Yes. Yeah.
Okay, we'll have one last question because we're a little bit over time. But if you were looking for evidence of life, what would we be looking for in the rocks?
Yes. So there are lots of different things we can look for. And I think it's more from a chemistry side, where we want to look for minerals that tend to form in certain environments. So minerals that may have formed in warm water is usually a good or a positive thing. It's not necessarily evidence, but any sort of minerals that might require life to interact with them. So for example, certain compounds on Earth are produced by bacteria, and you can see that in the rock record through chemical analysis. And then from more of an imaging standpoint, it's really difficult using remote sensing because it's really low resolution when you think about it. So our highest resolution is 12.5 centimeters, which is quite big. So it's more down to rovers seeing whether you can see any sort of fossil life. So always looking at pebbles and different sort of shapes of rocks for physical fossils, but most of it is down to the chemistry. Yeah.
Okay, well, I think we'll leave it there. That was really fascinating. So good. I hope everyone now goes away and has a research into the planetary geology. Thank you everyone for joining. This series is called Lunchtime Scientist, and we've been talking to working scientists every Wednesday at 1 o'clock. Our next one is going to be held by the Society of Antiquaries, so you can keep up to date on the Geological Society social media. We'll be publishing the next one there. And you can rewatch the sessions from the Linnean Society and the Royal Astronomical Society if you head over to their YouTube channels. This is also going to be put onto YouTube, so if you want to share it with anyone afterwards, please feel free. And thank you so much, Divya. That was really, really interesting.
Thanks so much for having me.
All right, thank you. Goodbye, everyone.